Now, I've been saying for a while now that you can't tell precisely where an electron is because of its wave-like nature. Say you have a wave function for an electron that looks like this. The wave is spread out over a lot of locations. So you can't put your finger down in one place and say that's where the electron is. Now, on the other hand, if you've got a wave packet, like we've talked about before, the amplitude is related to the probability of where I can find the electrons. So I can see there's only one place really in here where the amplitude of the wave is big. It's a spike, it's like a pulse, and I can know that the electron is in here somewhere. So I can't tell where the electron is here, but I can tell where it is. Now, why do you have wave functions that look like this sometimes and wave functions that look like this sometimes? Well, you get a wave packet like this when you have several different wavelengths of electrons moving through. The electron might have several different possible wavelengths. So it might have, we don't know, it might have the blue one here, it might have the purple one, it might have the red one, and they're all moving through the same region of space, and they're going to interfere with each other. Where one is pulling down and the others are pulling up, they're going to be destructive interference. But notice that there's this point right here where they're all pulling up, and they're all going to constructively interfere right at that one point. And that produces the wave packet that we see up here. All right, now my point is, if I want to say what the wavelengths of these two things are, I can say that I know this one precisely, right? Because I can just get the peak-to-peak distance there. If I want to look at the wavelength of this one, though, since it really is interference of a lot of different wavelengths, I don't know which of those wavelengths is the right one. So I don't really know. I can average them, but I don't precisely know what the wavelength is. So when you have a wave packet where you know the location, let's call the location X. I don't know where the location is with this one, and I do know the location here. I don't know exactly, but I know it fairly precisely. Okay? Now, let's work momentum into this. The de Broglie equation says that wavelength is Planck's constant over the momentum, p. So if I'm going to add a p column here, momentum p, can I say that I know the momentum precisely or imprecisely for this wave? Well, I precisely know the wavelength for this wave. So I precisely know the momentum. Okay? Now, how about this wave? I don't really know the wavelength, so I don't really know the momentum. All right. So I have these two situations. One, I know the location, but I don't know the momentum. One, I don't know the location, but I do know the momentum. And momentum and position are what they call complementary variables. Complementary variables, because you can know one and then you're uncertain about the other. You can't know them both at the same time. That is a statement of the Heisenberg uncertainty principle. Let me write it down. You can't precisely know both location and momentum. When you have a quantum mechanical particle like an electron. Now, this works for other particles too. Anything that's small, like even an atom, will have this uncertainty principle applied to it. I'm going to just say electrons to keep it specific. So it works for any quantum mechanical particle, but especially for electrons. You can't know them both precisely at the same time. Put a box around this. This is a statement of the uncertainty principle. Now, did you ever see that show Breaking Bad? It was a show about a high school chemistry teacher who became a drug kingpin. And he adopted the alias Heisenberg, which is the name of this statement here, because he was sort of taunting the people that were trying to catch him. You couldn't know where he was if you knew what he was doing, and if you knew what he was doing, you didn't. If you knew where he was, you didn't know what he was doing. So it was kind of a play on the uncertainty principle here. That's why he called himself Heisenberg. The real Heisenberg was one of the architects of quantum mechanics, and he was in Nazi Germany. And he was not only an architect of quantum mechanics, but also one of the people that was helping them develop nuclear power and so atomic weapons during World War II. He didn't finish his project before the end of the war, which was a good thing for us. So let's look at this a little bit more closely, this uncertainty principle. In particular, it tells us something important. And that important thing is why atoms are the sizes that they are. If you write down the uncertainty principle in math, you can say the uncertainty in the location. This is the uncertainty in the location. That's what that symbol means. Times the uncertainty in the momentum. That's got to be bigger than or equal to a small number. The small number happens to be Planck's constant over 4 pi. This is the same Planck's constant that keeps on cropping up over and over again. It has a value of 6.626 times 10 to the minus 34 joules seconds. And it is a sign that you're doing quantum mechanics. You will only see Planck's constant appear in a quantum mechanical equation. This is the mathematical statement of the Heisenberg uncertainty principle. Now, let's use it to figure out why atoms are the sizes that they are. Why are they so small? Let's suppose that we are looking at the uncertainty in the position of an electron in a hydrogen atom. Let's say that the uncertainty here is r, the radius of the atom. So we're not sure where the electron is. We know it's somewhere in the atom, and we'll say it's give or take a radius of the atom. It's the uncertainty in the position. Now, what about this? Let's estimate the uncertainty in the momentum. Let's say that we know the momentum to give or take 4 figures. That would mean we'd know the speed of the electron to give or take 4 figures. We can calculate the speeds of things from the energies. So this is kind of a reasonable thing to do. So let's say you can calculate the uncertainty in the momentum. The momentum is mv. So the uncertainty in mv is going to be the mass times the uncertainty in the speed. It's going to be the mass of the electron. It happens to have a value of 9.1 times 10 to the minus 31 kilograms, times the uncertainty in the speed. Let's say it's about 0.5%. of the speed of light. C is the speed of light. So let's say that my uncertainty is going to be, in the speed, is going to be about half of a percent of the speed of light. That's a reasonable uncertainty. And in fact, we find we can't measure the speed of the electron any better than that. So let's put a number in for that, okay? It's going to be 0.005, because that's what half a percent is. 0.005 times the speed of light. Let's say the speed of light is 2.9979 times 10 to the 8 meters per second. I'm trying to avoid that glare spot there. Let's go ahead and do the math. 9.1 EE minus 31 times 0.005 times 2.9979 EE8 gives me 1.36 times 10 to the minus 24. Now, really, I'm not going to have any better than one figure here because I've only had this into one figure, but let's keep the extra figures. How about the units? Kilograms times meters per second. So there's my uncertainty in delta P. That is my uncertainty delta P in the momentum. All right, I want to figure out what the radius of the atom is going to be. If I put an R in instead of delta X, and I put this number in instead of delta P, I'm going to have R times this is greater than or equal to this small number here. Or I can write R is greater than or equal to H over 4 pi. And then I divide both sides of this equation, this inequality, by delta P. And I can figure it out. The radius of the atom has got to be greater than or equal to this. So this is kind of a minimum radius that the hydrogen atom could have. I'm going to plug in Planck's constant. Over 4 pi. And then let's put in this number for delta P that we just figured out up here. Whoops. Kilograms times meters per second. I'm asking you to do the rest of this equation, the rest of this calculation in the space below this video. Now, let's check. So you can do the math here to figure out what the radius is going to be bigger than. Let's do just a quick check on my math here to make sure that I have everything right. Okay, how about the units? When I'm trying to check a calculation, I want to make sure that the units are coming out right. That is something we learned in Module 1 with the unit conversion thing. So what should my units come out to be? The units ought to come out to be meters. Now, what are my units here? Well, I got joule seconds on top. And I got kilogram meters per second on the bottom. Now, let's see if we can simplify this to meters. Okay, I know the definition of a joule. A joule is, from Module 1, kilogram meters squared per second squared. So, if I write that in, I'm going to have kilogram meters squared per second squared times seconds over kilogram meters per second. Okay, This looks pretty wretched. Let's simplify it. If I look at the seconds, I have seconds divided by seconds squared, so that'll be 1 over seconds on the top, right? And now if I multiply the top and the bottom by seconds, that gets rid of the seconds. Now I can see there's kilograms divided by kilograms. And now there's meters squared divided by meters, which is meters. So the units came out right. That means that I did my math right, at least as far as the numbers might be wrong, but I did I did the algebra correctly because I'm getting the right units out of here. So I passed my unit check. I'm getting meters out of here. Roughly, what's the size of this? Okay, well, let's see if we can do it in our heads. We've got 6.626 times 10 to the minus 34 divided by 4 divided by pi divided by this whole mess. Okay, so what am I going to get here? Let's factor all of this stuff out, and I get something that's, let's call this 7. 7 over 4 over pi over 1.4 times 10 to the minus 34 over 10 to the minus 24. This is 24 here. That was what I figured out here. 20 minus 24. Okay. Now 10 to the minus 34 divided by 10 to the minus 24 is 10 to the minus 34 plus 24. So it'll be 10 to the minus 10. Okay, and what's this mess going to be? Well, let me see. This is like 7 divided by 4 times, say pi is 3. Times 3 times, say that's 1.5. Okay, so what would that be? That would be like 12, 1.5 times 12 is going to be like 18. So it's like 7/18. So it's going to be like a little bit less than 0.5 here. So a little less than 0.5. So I'm going to be getting what? Something like, if I turn this into scientific notation. See what I did there? I made this 10 times bigger to make it scientific notation. So I had to make this one 10 times smaller. So I'm getting a radius, a minimum radius for the hydrogen atom that looks something like that. That's about 50 picometers if I go ahead and convert it into picometers. A picometer is 10 to the minus 12 meters. So this is 50 of those. And guess what the true radius of a hydrogen atom is? It's about 53 picometers. So I'm just about right. So my point here with this calculation is that you are predicting the size of an atom by the uncertainty principle. The uncertainty principle is what keeps the electron from just falling into the nucleus and sticking there. This resolves the collapsing atom paradox. The uncertainty principle is the resolution of that. So the electron is not just a particle orbiting around the nucleus. The electron is a wave. And if you use the wave as a probability of locating the particle, you can see that your uncertainty in the location is such that you cannot say for sure, ever, that the electron is trapped inside the nucleus.